Hello all, I want to quickly do section 4.4. There's actually not really a note for 4.4 because it's the same as what we've been doing in 4.2 and 3 where F net equals ma. But in previous questions, F net was based upon forces that were in a single plane, in other words in one dimension. In 4.4 we get into forces being applied in two dimensions. So the easiest way to do this is to basically rattle through a couple of sample questions so you get the idea, and then assign some for you to try. Alright, so for sample number 4, they've got people sitting around a Ouija board. Ouija board is if you've never seen one, you've got an item which is on the center of the table, and 4 people basically are applying forces in perpendicular directions. So you can see that it's a 0.2 kilogram object, and the 4 people are applying these 4 different forces. Now I have to analyze these forces because they're perpendicular. It's kind of nice because I can look at them as if they are components of a right angle triangle. So if I look at the left and right forces here, this force and this force, I can see that the force, I'm going to call it, even though it's on a horizontal table, let's say left and right, is 2 newtons left and 1.2 newtons right. So I'm going to get 0.8 newtons to the left. If I look at the forces that seem to be going up and down or across the table, so the force up and down, even though it's not vertically up and down, I'm getting 0.6 newtons to the direction, which is that direction across the table. So you can see that when I've added the 2 forces in this plane and the 2 forces in the other plane, I can come up with a net force in both of the directions, and then I can say, well, ultimately, if the left and right forces become this, and the up and down forces become this, it means all 4 forces together are going to have a final summative force, which goes left 0.8, and this way by a little bit less, which is 0.6. So the direction for the net force is this direction. And to solve for the F net, right, the question is asking what is F net and what is the acceleration of the object. To solve for F net, I'm going to use Pythagorean theorem, and I get exactly 1.0, right? Let's just call that F net. Which is equal to the square root of 0.6 squared plus 0.8 squared, which is exactly 1.0 newtons. And then if I say what direction is that puck going to move, or that object going to move, it's going to move to the left, and then let's say down if I'm using that as my direction, left and down by some angle theta degrees. And because it's a right angle triangle, as we can see here, right, I know that I can use, my theta doesn't look very good, I can use tan of theta is equal to the ratio of the opposite, SOHCAHTOA, tan theta equals opposite over adjacent, SOHCAHTOA. Theta works out to be 37 degrees. So my direction for F net, because remember F net is a vector quantity, is going to be 1 newton in a direction which is this way, and then turn 37 degrees this way. Okay, notice I'm not using north, south, east, west here, because it doesn't matter which way the game is going, unless you ultimately decided to call the directions north, south, east, west, right? And then you could use north, south, east, west. You could say that it's going east 37 degrees south. All right, so there's your F net. And then the question also asks for the acceleration. So if I want to solve for the acceleration here, I know that the F net is equal to MA. The F net is 1.0 newtons. The mass was, I believe, 0.2 kilograms. And I can solve for the acceleration, which turns out to be 5.0 meters per second squared. But again, remember, acceleration is also a vector quantity, so it has direction which says go this way and turn 37 degrees this way. Okay, and that's the other half of that question. All right, so that one's pretty straightforward. Right? You got to hate when I say that, because you know what's coming is probably not so straightforward. Okay, the second question has two people pulling on a toboggan across a horizontal surface. Now, the toboggan, if I'm looking down at the toboggan, so this is sample question number 5. Which is in your textbook on page 133. Now, if I'm looking down at the toboggan from above, right, here's the top of the toboggan. Okay, here's the person sitting on the toboggan with their legs out and their arms out, sitting on the toboggan, and the two forces are being applied by person 1 and person 2. Right, so this is force because of person 1. This is the force because of person 2. Now, we're told that the forces are being applied in this direction, which is 40 degrees. My stylus is just not working here. 40 degrees away from, again, let's say that direction is east. Right? And force number 2 is being applied in this direction, which is 25 degrees south of east. Now, the two forces that are being applied are, the first person is applying 50 newtons of force, and the second person is applying 60 newtons of force. Okay, so those are the forces that are being applied. Now notice, if I was to ignore person 2 here for a minute, it's not very nice of me, and look at what person 1 is doing, person 1 is pulling the person in two directions, pulling the person north and east. And person number 2 is pulling the person south and east also. So just like I did in the last question, if I can figure out how much my norths, souths, and easts are, I can calculate using my component method by breaking down the two F1 and F2 forces into their separate north-south and east-west components. I can come up with a final answer. We're told that the person has a mass of 70 kilograms. And the question is, what is F net and what is the person's acceleration? Now, let's look at F1 for a minute. So let's just push this up and let's look at F1. So F1, okay, I'm going to actually redraw it here. F1 is pulling the person 40 degrees east and north. And this was 50 newtons. So my north component is going to be 50 opposite SOHCAHTOA sine of 40 degrees, and my east is going to be SOHCAHTOA 50 cosine of 40 degrees. Now if I do my math, I'm getting 38 newtons. I'm going to leave an extra decimal in here for now. 38.3 newtons east. And if I look at the far side, 40 sine times the force, I'm getting 32.1 newtons north. If I look at my second vector is pulling the person east and south such that there is a 25-degree angle in here, and the magnitude of this force is 60. So I have an east force here and a south force here. My east force is going to be the hypotenuse times the cosine of 25 degrees. My south is going to be hypotenuse, opposite, so katoa, sine of 25 degrees. Now, if I quickly do the math here, 25 sine times 60, I'm getting 25.4 newtons. And if I look at my east vector, I'm getting 54.4 newtons. Okay, so if I continue to look at the components, I see I have a north of 32.1 and a south of 25.4. So if I look at my force in the north-south plane, I have 32.1 newtons north, and I have 25.4 newtons south. Again, if I use north as positive and south as negative, when I add them together, I will get 6.7 newtons north. If I look at my east-west components, which is all east, I'm going to have 38.3 newtons east, plus another 54.4 newtons east, and I get 54 and 38 is 4292.7 newtons east. Okay, so now that I know my components, I can add them together, because I know that I have 92.7 east and I have 6.7 north. So my summative vector from all of those components, again remember the four components are basically parts of the two initial vectors, right, are going to give me my final F net. Okay, I'm going to use Pythagoras. Right. And if I take my 92.7 squared plus my 6.7 squared and take the square root, I'm getting 92.9. And my direction, again, remember that we originally chose north, south, east, west, so it's going to be east theta degrees north. I can find theta using tan because I see I have an opposite and an adjacent side of a right angle triangle, right? And ultimately, tan theta is equal to opposite divided by adjacent. Theta turns out to be a small angle, 4.1 degrees. So if I look at my F net here now, up here, I can see that it's 92.9 newtons in a direction which is east 4.1 degrees north. And that's my final answer. Now, the other way to solve this problem is using your trig laws, your sine laws and your cosine laws. So if I want to solve this again, but using my trig laws, I'm going to add my two forces directly. Instead of breaking the forces down and adding them, I'm just going to add them directly. So I have two forces acting here. The first force, if I start here, the first force is 40 degrees north of east. Whoops. And my second force is 25 degrees south of east. Now, I know this vector here is 50 newtons, and this vector here is 60 newtons. So my final answer, after I add these two vectors up, again, notice this one should be longer than the other one, but because this angle here is so much smaller than this angle here, I'm guessing, I could be wrong, but I'm guessing that the final answer is going to look something like this. Now, I know that the final answer will be less than 110 because 50 and 60 are coming together, and I know that the angle, if I've drawn this right, should have an angle theta, which is east and a small number of degrees to the north. Now, we already know from our previous question, or previous solution, that is 4 degrees. Okay, but for now, let's pretend we don't already know the answer for the other direction. Okay, so to do this trig law, my cosine law, I need to solve f net here using my cosine law. For the cosine law, I need to know two opposite sides, which I do, and I need to know the inside angle here, which I also know. I think, well, hang on, no, we don't know that one. Well, we do know that one. If I know that this side is 25 degrees over here, this side is 25 degrees over here, and I know that, come on, this angle is 40 here, then I know that this, oh darn it, I know that this is 40 in here also. Right, Z pattern. Okay, I have an east-west line down here. I have an east-west line here, and I have an east-west line here. Right? So there's my Z pattern. And if I know this is 40 down here, that will be 40 up there. Now, if I know, let's go to a different color still. If I know that this is 40 and this is 25, that's 65 degrees. I know that the inside angle has to make up to 180 because from my west side to my east side has to be 180 degrees. So if I have 65, that's 115 degrees. So now I can do my F net squared equals the two sides, 50 squared plus 60 squared minus 2 times 50 times 60 times the cosine of my inside angle, 115 degrees. Okay, and I'm hoping that I'm going to get, what did I have before? Oh, darn it. I had 92.9 newtons. Let's see what we get here now. So I'm going to start at the end, 115, and do my cosine times 60 times 50, 60 times 50 times negative 2 plus 50 squared plus 60 squared equals, and square root, I'm getting 92.9 newtons. Right. And then I need to solve for my angle. You think it's 40 degrees. Well, it's not 40 degrees. Right? I'm looking at the angle inside here. Right, between the dotted line that goes up, which is my F net, and the line below it, which is my east-west line. So there's going to be some, again, if I've drawn this right, it should be an angle between, which is a small angle, maybe just north of east or just west of east, depending on how this works out. So now I can do my cosine law. I can solve for, let's pick a different color again. I can solve for this angle in here because I know I can do my sine law. The sine law is going to say, just move this up a little bit, that sine of 115 degrees divided by its opposite side, F net, is equal to the sine of my new angle, unknown angle theta, divided by its opposite side, which is 60. Now if I do the math, okay, I've got 115 sine times 60 divided by 92.9 and shift sine, whoops, 115 sine times 60 divided by 92.9. Get 35.8 degrees. Okay, 35.8 degrees. So what that's telling me is that this angle here is 35.8 degrees. Oh, but I know that this whole angle was 40. So if I try to solve for the little angle that's in here again, it's going to be 40 minus 35.8. So if I call this little angle in here angle X, then I know that angle X is going to be 40 minus 35.8, which is 4.2 degrees. So my F net is going to be 92.9 newtons in a direction which is east 4.2 degrees to the north. Whoops. My page is not going to work here. Not going to let me do this. 4.2 degrees to the north. And my square brackets. Okay, which is exactly the same answer we had before. So you can decide whether you want to do the work of breaking the question, breaking your vectors down into their components, analyzing each vector here. This one, using my sine and cosine functions to come up with components. And then once you know your components, drawing a final answer. Then using your Pythagorean theorem and your trig functions to find your net force and your angles. I think that might almost be the easiest way to do it. But again, if you're comfortable with the cosine, there's a lot more steps there than the other way. This is, you can see, a much shorter solution and probably ultimately might even be less prone to making mistakes. But again, it's your call because you should get the same answer both ways. All right, so that being said, that's all I really have for 4.4. If I switch out of here and go back to my notes for 4.4, so I've just done the two sample questions here on 131 to 135 in the textbook. I'm going to leave you with question 1 on page 135 and with the questions on page 147. Right, so I hope that makes sense, and like I said, you've got some options, but again, we're just doing F net equals ma again. Oh, actually, the question that I was just doing was asking me for acceleration, so you know what, let's just finish the acceleration. If I finish the acceleration there, however you get that final answer, the acceleration F net is 92.9 newtons. 92.9 is equal to ma. Mass was 70 kilograms. So the acceleration is 92.9 divided by 70, which is 1.3 meters per second squared. Again, remember, this is a vector quantity in a direction which is east 4.2 or 4.3 degrees